everybody. Now that we've been through formula writing and naming of ionic compounds, covalent compounds, diatomics, and acids, we are now ready to write and balance equations. We're going to take all of those individual pieces that we've picked up along the way and now put them together into something meaningful, showing how reactants, how substances that react together are going to react to form or produce products. Let's go ahead and get started. The first thing we have to look at are the three ways of writing equations. First, we're often going to be given a sentence that represents some kind of scientific event, and we call that a word equation. So it's nothing more than words describing a reaction. A sentence will clearly identify your reactants and your products, and we learned that those were the things that we started with and the things that we finished with. So reactants always begin a reaction, products always finish a reaction. And you can compare it to making food following a recipe in your kitchen. All of the initial ingredients that you put in are your reactants, and your final product when you're done is going to be your finished dish. So when we do this in chemistry, though, we're going to watch out for some key words that are some giveaways that are going to play a part in this writing and balancing of equations. Words like yield. When you see the word yield, it means two reactants have come together to form something, and what you're going to see is an arrow. Sometimes you'll even see a double arrow, which means that the reaction goes in both directions. More on that later. We also see react to form, which is another way of just representing producing products, and it's the same thing as yield. We're just going to use an arrow for that. Decomposes is yet another one, but in this case, a big substance is going to break into smaller substances. However, in the equation, we're still going to use an arrow to represent it. The word and in chemistry is going to be represented by the symbol plus. So if you have two chemicals, something and something else, you'd put a plus in between the two of them, either they're reactants or products. So here we have an example. It says, during electrolysis, water decomposes into hydrogen and oxygen gases. Okay, so the first thing they do here is they kind of tip you off at what the process is. Now, that's not going to play a part in our writing of this equation, but we do see water decomposing into hydrogen and oxygen gases. So what we're going to do here is we're going to represent those words with formulas. And as we all know, water is H2O. When we are in the business of representing words that are going to translate into equations, we try to put the state of matter in there as well. So in the case of water, we're just going to have the state of matter of liquid. And how we represent that is with a cursive lowercase l in parentheses. Now, here's that word decomposes. So what that means is we're next going to have an arrow representing that this is breaking down into, and then we can see our two products over here. So this is our only reactant. There's only one in this case, and these are our products. So, hydrogen and oxygen gases, these products here, they each have a formula. And if you remember your diatomics, you're going to remember that hydrogen is not just H, okay? A lot of students just want to put H. But what an H does, it gets you this. Here's an H with a single valence electron. So the question is this thing stable? And the answer is no. Hydrogen must have two electrons to be stable, and the way it gets there is by finding another hydrogen to bond with, and then each hydrogen now has two electrons, and that's why the formula is H2. Now, hydrogen at room temperature is also in the form of a gas, so we're going to put lowercase g in parentheses, and here is that word and, so like we said before, and will be represented by a plus. And then oxygen gases, one more time, oxygen is not just O, because if it was just O, it would have not 8 electrons, but 6, okay? And having 6 electrons is not a stable state for oxygen. So instead, another oxygen is going to come and bond with it, and instead of having just O, we have O2. Right now, you're breathing in O2 gas, not O. And O2 at room temperature is also gaseous, so we're going to put a lowercase g. So what we've done here is we've represented this equation into what's called a skeleton. So in a skeleton equation, We use chemical formulas rather than words to identify the reactants and products. We will also note the state of matter with a symbol after each chemical formula. And that's exactly what we did there. So we go from a word equation, a written description of this reaction, into actual formulas. So in the case here, this is what we just wrote down. We have water as a liquid. It's being decomposed into hydrogen gas and oxygen gas. Obviously, this looks nice and neat compared to my handwriting, but that's okay. Next, we go from a skeleton equation into what's called a balanced equation. And here's why. If we take a closer look at water breaking into hydrogen gas and oxygen gas, notice how many atoms you find in the reactants versus the products. So in the case of hydrogen, we see 2 here. And in the case of the products, we also see 2 hydrogen. Now in chemistry, that's good. If you have the same amount on both sides, that's exactly what we want. Because you can't just have matter suddenly appear into a reaction or suddenly disappear from a reaction. But if we take a look at the oxygen, here we have 1, which is part of the water molecule, and over here we have 2. Now, in a skeleton, you're going to find that quite often that it doesn't balance out. You're going to have different numbers of one thing versus the other, of one thing on one side versus the other side. And what we're going to do with a balanced chemical equation, which is coming next, is we're going to factor in that the left side of the equation, on the left of the arrow, must equal what's on the right of the arrow. And we do that by changing coefficients. You remember from math class, a coefficient sits in front of your variable. Well, in chemistry, we have the same thing going on. Your coefficient is a number that sits in front of the formula. So in the case of water breaking down into those 2 things, let's rewrite it real quick down here. If you have something to write with yourself, go ahead and do it with me. We have H2O, and just for right now, I'm going to leave out the state of matter. It's decomposing into H2 and O2. Now, the 2 hydrogens on each side is great. It works very well for us. But with the O's, we have 1 on the left and we have 2 on the right. So how we remedy that is by using a coefficient. So what I'm going to do is I'm going to go way over here on the reactant side and put a 2. Because this 2 holds for everything behind it, which including that single O. So now I have 2 O's here, which balance with the 2 O's on your product side. Now, when I put the 2 here, something happened though with the other chemical. Here we have hydrogen. We had 2, but when we put a 2 in front of it, that means now we have 2 H2 molecules. So if this is an H2, H and H, and we have 2 molecules of each one of those, now we have 4 hydrogen atoms. When we balance equations, we're in the business of counting atoms. So on the left right now I have 4 hydrogen atoms, and on the right I have 2. So there's a quick remedy for that as well, which is put a 2 in front of this, and now I have 4 hydrogens on the left hand side, I have 4 hydrogens on the right. Here I have 2 oxygens on the left, and here I have 2 oxygens on the right. So in terms of writing and balancing equations, this one is set as 2 H2O yields or decomposes into 2 molecules of hydrogen, 2 molecules of H2, plus 1 molecule of O2. Chemical equations show the relative amounts of substances involved. So we have a ratio here of 2 to 2 to 1 of our chemical species that we find in this equation. The next thing that we have to understand is that you have had ionic compounds, covalent compounds, diatomics, and acids taught to you. So what that means is that you're expected to know how to do certain things when translating your word equation into your skeleton equation. So let's go over some of those key pieces. First, when translating a word equation, scan its name for a metal first. If a metal is first in the name and followed by a nonmetal, it's ionic. So you learned this in the ionic chapter. If you are weak at changing ionic names into formulas, one thing you should do is go back and review that material. I have a number of videos at my website at the Prof. Amen channel that you can check out, at least 5 or 6 videos where it reteaches that concept. So feel free to go check that out if you know you're weak there. If you think you can hang tough there, we can go ahead and look at some examples. I do want to throw in, if you find a Roman numeral in the name of your ionic compound, that Roman numeral represents the metal's positive charge. So if we have something like this, we have iron 3 oxide. What that's telling me is that my iron has a 3 plus charge, and oxide comes from oxygen, and we know that it has a 2 minus charge because it's group 16 or 6A. It needs 2 additional electrons to be stable. That's why it forms a 2 minus charge. Now, as you know, in ionic compounds, they must balance to equal 0. So the question is, does a 3 plus and a 2 minus equal 0? And hopefully your answer is no. What we have to do then, and this can be done different ways. It can be done mentally, or it can be done using the crisscross method. Crisscross method is where you change the ion charges, you cross them diagonally or crisscross them, and those charges now become your subscripts. So what this becomes then is Fe will now be followed by the number 2, and we always keep subscripts positive, and O will be followed by the 3 plus charge, which is just a 3. So the formula for iron 3 oxide is Fe2O3. You have to be able to do that with many different compounds in order to be successful at writing and balancing equations. It's a must. Number 2, if a nonmetal comes first in the compound that you're trying to translate, it's likely you have a covalent compound. Write its formula accordingly. So this is where most students do just fine with. In the case of dinitrogen pentoxide, as long as you've memorized those prefixes for the covalent compounds, you're going to be just fine. Di means the number 2. So it's dinitrogen, so N will be followed by a 2. And pent, if you remember that prefix, represents the number 5. So it's pentoxide, which represents oxygen. So I have an O, and I'm going to put a 5 behind it. So this way of writing formulas is very easy when you translate, as long as you've memorized those prefixes for covalent compounds. If you haven't, it won't take long. Go back and review that before you start balancing equations. Number 3. If hydrogen comes first in your compound, you likely have an acid. Use your acid naming rules to decode the formula. So however you name acids, you're going to kind of go backwards as you try to translate the words into a formula. Let me give you an example. Hydrochloric acid. Now, in acid naming rules, we use the prefix hydro when naming a binary acid, when you have hydrogen with one other element. So here, this represents hydrogen, and this represents another element. And hopefully, your guess on that from chloric would be chlorine. So what we have then is a formula that just has 2 elements, and H is kind of your dead giveaway that it's going to be an acid, and then it's going to be followed by chlorine. So the formula for hydrochloric acid would be HCl. Now, the naming for oxyacids gets a little bit more difficult, so make sure that you go back and review how to do those, because you will come across those as well as you try to write and balance your equations. And last but not least, super important, there are a number of diatomic molecules, and those are HON and the halogens. So anytime you have any of these particular elements in Chem 1, you know that you're going to have a diatomic molecule. Let's look at liquid bromine. Now, bromine's not hydrogen, oxygen, or nitrogen, but it is one of the halogens, and all of the halogens have a diatomic subscript of 2 behind it. So liquid bromine would be Br with a little 2 as a subscript, and this one's a liquid, so we're going to use the lowercase cursive L. Okay, one more time on why bromine has to be diatomic. If we put its valence electrons around it, it's a group 17 or 7A, and it has 7 valence electrons, and this is unhappy. So it takes another bromine coming in with its 7 in order to make both of them happy. And that is how you get Br2. So hopefully you can remember HON and the halogens are your diatomics. And that's going to make a difference when you try balancing these equations. Because if any one of these four big steps here are off, it's going to lead to nearly an impossible task to balance a formula correctly. Next, I want to look at some general steps for balancing equations. Here we go. First, write your skeleton equation out. Translate that word equation into meaningful formulas, correct formulas. So make sure that you do your reviews for ionic compounds, covalent compounds, acid writing formulas, and diatomics. When you write your skeleton, use arrows, use those pluses for the word and the physical states, solid, liquid, gas, and aqueous. Number 2, count the number of atoms per element in the reactants. 3, count the number of atoms per element in the products. Now, your reactants are typically in Chem 1 going to be always found on the left-hand side of the arrows. So we are in the atom counting business. So we don't violate the law of conservation. We got to count and make sure you have the same number of things on the left in terms of atoms as on the right. That's why 2 and 3 are very closely related, and they happen almost simultaneously when you're balancing. Number 4, change the coefficients to make the number of atoms on both sides of the equation equal. You're in the business of changing numbers in front of chemicals in order for those chemical equations to be balanced properly. Sometimes you got to go back and forth, changing the number a number of times. Not everybody's perfect. You're not going to get it on the first time. And the last thing I should throw in here as a side note is use a pencil when you balance. Do not try to do this in pen, or your paper will be a big mess by the time you're finished. A lot of the equations with that back and forth writing is going to cause you to erase 3, 4, 5 times. Number 5, if you wind up with coefficients that do balance out that equation, reduce them down into the lowest possible ratio. So if you wind up with coefficients of 2, 4, 4, 2, you know that all 4 of those numbers are divisible by 2, so it would be 1, 2, 2, 1 instead. The last thing, and I can't stress this one the most, you see it down here at the bottom, never change subscripts of formulas, okay? So a formula for a chemical is what it is. You cannot get inside of that formula and start changing those numbers around, because then you're changing the chemical, usually to something that doesn't exist. So the only thing you're allowed to change are those coefficients. Let's go ahead and take a look at an example, and we'll kind of go through the steps on the fly so you can see how this is done. So our word equation here, again, are words that represent a chemical event happening. When solid iron and fluorine gas are put together in a reaction vessel, they react to form iron 3 fluoride. Okay, so our first job is to write the skeleton. Okay, and the skeleton is unbalanced, but it's us changing these words into meaningful, accurate formulas. So first, solid iron. Now, there's nothing with the iron, so then I just look at the periodic table. I find that iron symbol is Fe, and I do notice that it does give me the state of matter, solid, so I'm just going to put a little lowercase s there. Here is that word and, so that represents a plus, and here it says fluorine gas. Now, if someone's not thinking, what they're going to do is say, oh, fluorine gas, all right, I'm going to put an F there with a G after it. But they'd be wrong. Why would they be wrong? Because fluorine's a halogen. It's a group 17 element. So if you don't have your periodic table out sitting in front of you and you don't know that, you're going to wind up getting this wrong, okay? So make sure that periodic table is like your best friend when you try to do these, sitting right to your right or to your left, whatever's more comfortable. And then you're going to get something like this correct, because you're going to put F2 to represent fluorine gas. And I'll put a little lowercase g after it there, nice and small, so it doesn't visually get in my way. And they react to form, which is my next thing I need to recognize as an action word, meaning yield, and that's produces my arrow in the equation. And I see iron 3 fluoride. So once again, it's telling me that my iron has a 3 plus charge, and fluoride comes from fluorine. And since this thing has a metal that comes first, M, we know that this thing is what? It's ionic. So that means we got to balance this thing out. Now, fluorine as a group 17 has a 1 minus charge. Now, 1 minus charge and a 3 plus charge do not equal 0. And in ionic compounds, these two must equal 0. So again, in your head or using the crisscross method, you can go ahead and figure out what the true formula is. I'll use crisscross. So that's coming down there, that's going down there. And now I have Fe followed by a 1 minus. Now, when we have 1 as a subscript, we don't write it. We know there's 1 because we can see the Fe here. No need to put a 1 behind it. But we have F coming next, and that one will be followed by a new number, which is 3. So we have Fe plus F2 yields FeF3. Okay, now this one here doesn't give us an actual state of matter. However, with enough experience with chemistry, you start to take reasonable guesses at what it is, and this one here winds up being a solid. Okay, but for early learners of chemistry, you might not be capable of doing that yet. All right, now from the skeleton, we're going to go ahead and we're going to now change it to a chemical equation. And when you say chemical equation, what that means is that it's balanced. So what we're going to do is we're going to go ahead and we're going to count, okay? Let me go ahead and I'm going to cross this out, scribble this out the best I can so this trash isn't there as we try to count atoms. All right, so here we go. On the left-hand side of our equation, we have 1 Fe, and on the right-hand side of our equation, we have 1 Fe. So that's good. However, our second reactant of F2 means we have 2 fluorines, but here I have 3 fluorines. And there's no real easy way to go about 2 and 3 balancing it out except using the least common factor of the 2. And those of you probably remember from math class, least common factor is the number that is going to be a low number that both of them are can wind up being multiplied by to reach the same number. So in the case of 2 and 3, I think we all could agree the least common factor is going to be 6 between the two of them. So how do I get 6? I'm going to put a 3 in front. I'm not going to put F6 down there because we're not allowed to. You're not allowed to change subscripts. So a 3F2 gives me 6 Fs. And here, I'm going to put a 2 out in front because that's the only place I'm allowed to. 2 F3s is also 6. Now, in putting this 2 here, I changed something. I changed the number of FEs. So we went from 1 Fe to 2 Fes, which means now I got to go back and reflect on this first element of Fe here. There's only one of them, but I need 2 of them, so I'm going to throw a 2 out in front there. So now it looks like we may be balanced. Let's go ahead and make sure. 2 Fes on the left, 2 Fes on the right. 6 Fs on the left, 2 times 3 is 6 Fs on the right. So what we do now is we finalize, instead of leaving a whole bunch of scribble there, we go ahead and we write our final balanced equation. 2Fe with a lowercase s plus 3F2 with a lowercase g. Then we have our yield arrow, and we have 2Fe F3, and that's a solid. So this would be our chemical equation, which is properly balanced. The last thing I want to leave you with are some hints for challenging balances. Sometimes you're going to wind up going back and forth, and the numbers keep changing as you try to figure out some magical coefficients that are going to make your equation work out. So let me just throw some things out there, and you can copy these down, hit pause, and do some copying, because I really do think they're going to benefit most people who are new to balancing equations. Number 1 would be try starting with an element that appears in only one spot on both sides of the equation. Eventually, you're going to get something called a double replacement reaction, and there's a lot going on there. So if you can find one that just appears in one spot on both sides of the equation, maybe start with that. There's no rules to which ones you start with. You can kind of pick and choose, and if you can't get a working balance starting with one element, choose a different element. Go to a different one, and maybe the thing will work out differently. Number 2, elements that you do see a lot in that are like in every chemical. Oxygen is one that's like that. Hydrogen often. Do it towards the end of the balance. Number 3, Break up polyatomic ions into their separate elements when you count those atoms. Remember, we're in the business of counting atoms left side versus right side. So a polyatomic ion like phosphate, PO4, with a 3- charge, we've been told keep them together as a group. The whole group carries a 3- charge. It is, sure, absolutely, when we're writing ionic equations, but now we're in the business of counting atoms. So a phosphate, when you're into writing and balancing equations, is 1P and 4 O's. That's how we look at phosphate. Number 4, save pure elements for last. So if you see just a single element hanging out, maybe it's some metal atom like aluminum or magnesium or chromium, or you see a gas that's diatomic, those are usually pretty easy to hit up at the very end for a final balancing effort. So maybe save those to the last. So I hope this helped you at least get a look at and try to get a feel for how to write and balance an equation. You'll have plenty of practice in class to do this. So I'll talk to you next time. See ya.